bond energies, all right? We're going to talk basics about the bonds first, and then we will go into the actual process of it. Okay, like I said, I think the beginning of this is a little vocabulary heavy, but we'll get into the process, which makes a little bit more sense. So if we break bonds, we've got to have energy added to the system, right? We have to have energy added to the system. I think that should be a common sense, right? If I want those bonds to break, I've got to get the molecules in motion, right? I've got to get them moving, and I've got to have enough energy to break that bond, okay? Because that's what happens when we add heat, right? They start moving, vibrating, and then they break. So we've got to have bonds, we've got to have energy added to the system. If I'm going to form bond, then we release energy from that system. Those should feel like they fit together because they are opposites, right? Formation and breaking of that bond. Okay. Your delta H here is given with this fancy formula, okay? Which is not so fancy when you really look at it. But I want you to see here, it's the, you know what this Greek letter means?
E.
Nope.
Alpha, beta, gamma,
Epsilon. Sigma, very close, okay, very close. Sigma, and it means the sum of, okay? It just means the sum of all the things, okay? So this is the sum of the energy required to break bonds and form new bonds. That's what our delta H is, the sum of the energy required to break the bonds and to form new bonds. Sigma is the sum of all the terms. So all the reactants added together, all the products added together, okay? So if I'm looking at this big fancy reaction, essentially what I'm saying is to calculate the enthalpy change in our reaction, we're going to take the sum of the energy of the reactants minus the sum of the energy of the products. Pretty simple, right? Okay, big fancy formula, but not such a big deal, okay? N always represents the number of moles. So we're looking at mole ratio here. We're checking our coefficients to make sure, because the values we use to calculate these energies are always given per mole. So if our mole ratio is different, we have to change that number that goes with it. Agreed? Yes, no. Okay. Then D represents the bond energy per mole. So like I said, it'll give us the energy of a particular type of bond. We will see how many moles of that bond we have. We will add up all of the reactants. We will subtract out all of the products, and that will give us our delta H. Okay, so fancy formula, not fancy work. Capiche? Okay, let's try one. Now, here's where it gets a little trickier, okay? Here's our reaction. This is just a smidge. Here's our reaction. And here's what we're going to. Okay, all that's happening is an atom is switching spots. You see how this N and this C just switch spots here? Okay, but we have to figure out what types of bonds are in those compounds. We've got to figure out, are they single bonds between carbon and hydrogen? Are they double bonds between carbon and hydrogen? We have to know what types of bonds we're breaking and what types of bonds we're forming. Because the energies we use are the energies found within the bonds. So we've got to be able to draw Lewis structures correctly. Right? That's why we introduced Lewis structures at the beginning of the chapter again. Okay? So, in order to do that, let's go Lewis structures first. Okay? So let's start with this guy. You see how they drew you a triple bond here? They even gave you a clue on the skeleton. Right? How nice. How nice. Even though I'm sure we could have figured it out ourselves. Well, okay. All right, let's try. Let's draw the Lewis structure for this guy. Okay, CH3NC. So let's count valence electrons first. Valence electrons would be 4 plus 3 plus, how many does nitrogen give us? 5 plus carbon is 4 more. That gives us 8. I think 16 electrons we need in our structure. Agreed? Okay, it gives us a clue about the skeleton here. Okay, CH3 bonded to a nitrogen, then it even tells you it's going to be triple bonded to that carbon. You see what I'm saying? It gives us a clue on the skeleton. So let's go ahead and finish the rest of those bonds. Let me make my bonds a different color here. Okay, it told us triple bond. So that's 2, 4, 6, 8, 10, 12, 14. Where do we see another issue here?
Carbon.
Carbon's octet is not full. So what do we have to do? Like that?
No. Can you run longer?
Yeah. Carbon doesn't love it, because remember, what does carbon love to have? It loves 4 bonds. But
It'll be okay.
it's going to survive, okay? Yep, it's going to make it, okay? So now we're gonna examine these types of bonds here and figure out what types of bonds we have, how many of them we have, to figure out what's the energy that is needed to break all of those bonds in our reactant side. Okay? So I kind of make myself a little list here at the bottom when I'm doing this problem. I would say I've got some CH single bonds. Agreed? How many of them do I have? 3. Okay, so I'm going to rewrite my list over here because I'm going to have to do it for both sides. So I've got 3 of them. Okay. Each of them has an energy of 413. So I'm going to take that times 3. Okay, I'm going to have to make my writing here a little smaller. Or give myself room somewhere else. What's this box over here? Yeah. Yeah, it was, but I can get rid of it. What is this? I'll just give myself a lot more space here. Okay. I am all powerful, Hannah. I'm just white painting over it. Okay, now I got some room. Okay. So we said we've got CH bonds and we have 3 of them. So 413 times 3. And so tell me what that number is. Run that in your calculator.
1,239.
Okay. Is that the only type of bond we've got in that molecule? No. What else do we have? CN single?
Yeah.
CN single is 305. Okay. And we've only got 1 of them, right? What other bonds do we have? CN, but
we also have a CC.
triple.
We don't have a CC though.
Nope, ignore me.
It's listed there because maybe we need it on the product side, but we don't need it right now. Okay, so CN triple gives me an energy of 891. You see how much more energy is required to break that triple bond than to break the single bond? Does that make sense? Right? That should make sense to us that it's going to take more energy to do that. So I think that's all the bonds accounted for on that reactant side. Would we agree? Yep. We took care of this one. We took care of this one, this. So I think we should be good there. Let's add up that reactant side.
2, 4, 3, 5.
1239 plus 305 plus 891 gives me a total of 2435 kilojoules. Okay, kilojoules. And you'll notice here that I didn't have a mole ratio, right? I didn't have a coefficient there. Had I had a coefficient, that would have, like, let's say if this was a 2, that would have doubled all those numbers, right? Because I would have had to do it twice. I would have had 2 of those molecules. So you could double it at the end. Great question. Always working smarter, Carly. I love it. Okay. Let's look now at the products side. Okay, we've got to draw this molecule now. Okay, we've got to draw the molecule that's listed here. Again, it gives us a clue about our skeleton, but we've got a CH3 bonded to a C and then bonded to an N. Okay, so those are just really switching spots.
And the lone pair's going on nitrogen?
Yeah, so this is, let's talk about why. You know, why does this reaction take place? Which one makes the atoms happier? This first one or the second one? The second one, right? Everyone gets their preference in the second one. Nitrogen wants 3 bonds, 1 pair. Carbon wants 4 bonds, right? So they're making that switch, and it makes everyone happy.
Why can't you put the lone pair on nitrogen in the first one?
Well, if you did that in the first guy, then nitrogen would have too many, and carbon would have not enough.
Oh.
See what I'm saying?
Well, but no, carbon has too many nitrogens.
Where? Right here?
No, carbon has just what it wants.
In the left one.
No, yeah, you're right. It does carry a charge, minus, plus.
Oh.
So nobody's happy. But when we get over here in the product side, we don't have any charges. So this is better Lewis structure anyway.
Okay. But so on the last one, would you be able to put the lone pair on nitrogen? Would it matter?
No, you couldn't, because then nitrogen would have an expanded octet, which is not allowed.
Okay.
Right? Because it's not in the 3rd period or below. if you got rid of this and tried to put the lone pair there, nitrogen would now have a charge of 1, 2, 3, 4, 5, -1 and +1. But nitrogen's not allowed to have an expanded octet. So it wouldn't work. Because it's not in the third energy level. It doesn't have d orbitals.
Oh. Okay.
Yeah. So it wouldn't work.
Carbon does.
Carbon, no, but carbon doesn't have an expanded octet by putting it like this. Right? It's still an octet. 1, 2, 3, 4, 5. It's got an extra electron, but it doesn't need an extra orbital because it's still only got 8.
Still in the
Still fits the octet.
P.
Yeah. Yep.
Okay.
All right, so let's count our types of bonds and energies here. We've got carbon to hydrogen bonds again. How many of them? 413 times 3, which we already did. 1239. Okay, second type we've got carbon to carbon, which is 347. We only have one of them, and then we've got carbon triple bonded to nitrogen. That's how that came up with that. Okay, 891. So I'm gonna add those up.
2,400.
Okay.
I bet you do.
2,477. Now all we do is reactants minus products, and then that's it. So my delta H is equal to reactants minus products. So 2435 minus 2477.
42.
Negative 42, and my units would be kilojoules per mole.
It's gonna be negative.
Yep.
42.
Stop. Stop.
Pretty good, right?
Stop.
It's easy when the skeleton's given to you. No, ma'am, it will not always be.
So big.
It's the funnest. Look at this guy. All right, so now we've got 3 reactants and 3 products. 3 reactants, 3 products. Let's do it. Yes. You don't have to, but here's the thing. I'm not super worried about you completing all the lone pairs on like your outer atoms, right? As long as you feel like you've got the bonds right, that's what matters. So if you don't have to fill in all your outer octets, fine with me. Okay, so I'll show you what I mean as we go through here. But let's do Lewis structures for these ones. All right, CH4 is very simple. Agreed?
Yeah.
Right? CH4 is just that. I don't think we need to count valence electrons, right? I think we're understood that it's just CH, H, H. If you don't even need to draw them out, fine with me too. Okay, but let's just get them all drawn out first before we kind of identify what that looks like. Okay, Cl2 would be Cl bonded to Cl, and then don't my lone pairs just fit, right? But here's what I want you to look at. We got to be careful there. We got a 2 in front. So when we get to that energy part, we're going to have to do that too. Okay. Okay, so isn't F2 going to look exactly the same as Cl2?
Yes.
So I'm not going to bother drawing the electrons, but I've got 2 of them. Okay. Then I'm going to look at my products. I'll do those in a different color. F2Cl2. So we're going to have Cl, right? I can fill in the electrons, but I don't need to, right? Everybody gets what they want on that one. HF is very simple, just like that. I've got 2 of them. And then HCl are very simple. Okay? You're not going to need to draw the lone pairs on that one either, but we've got 2. Right? So all of these are really simple Lewis structures. Okay? Hopefully we're not tripped up on any of those Lewis structures. Agreed? Because they're all halogens, which want 3 lone pairs, 1 bond. And then carbon always wants 4 bonds. Okay? Yeah, they're all halogens. Okay? All right, so now let's start looking at our energies.
Oh boy.
All right. On the reactants side, C to H, single bonds are worth 413. And how many of them do I have?
4.
I have 4. Okay. I don't know what that is. Let's see here.
1, 2, 3, 9 plus 4, 13.
4, 13 times 4. 1652.
Good job, Martha.
All right, next type of bond I have is Cl to Cl, which is 239.
Do you have to multiply by 4 or 2 and then?
No, okay, I've only got one bond within the molecule, and I have two molecules, so I just multiply it by 2.
Oh.
Oh,
Right.
okay.
Does that make sense?
Yep.
Right? I'm only breaking one bond within that molecule, but I've got two molecules, so that's where my 2 comes in. Okay, fluorine to fluorine, I've got a single bond there that is 154, and I've got 2 of those bonds I need to break, which gives me 308. And that's it, right, for my reactant side? All right, on my products side, we have carbon to fluorine bonds, and they are 485. How many of those do I have?
2.
Times 2. Times 2, okay? 1 and 2 right there, okay? Then I've got carbon to chlorine, which is 339. Oh, I didn't finish that math problem. Whoops. 485 times 2. Am I going too fast, or are we hanging in there? Okay. Okay. I didn't have a coefficient up there, so I'm good to go on that one. Hydrogen to fluorine, that bond is 565. 2 of those bonds I have to break. 1130, and then hydrogen to chlorine is 427. I've got 2 of those. Now, I want you to look at something real quick. Did you notice how the bond energies with fluorine are higher in comparison to the bond energies with chlorine? Why do you think that is?
It's more electronegative.
Bingo, right? Fluorine's more electronegative. It wants electrons more than anyone else. Right? It's going to hold on to those things tighter. It doesn't want to break that bond, right? It wants its octet to be full. Very good. So that all of that ties together, right? All of that stuff with electronegativity ties together. So, okay, let's add them up.
Oh, I looked at the wrong one. Okay.
1652 plus 478 plus 3. 2438, I think, on the reactant side. And then on the product side,
Bam.
oops. $36.32 on the product side. Yes. Okay, so that gives me negative.
94. If I did it right.
I thought 1194.
Yeah,
I got
1194.
Did
Did you do 3,000 minus 200? The 2,000?
Maybe.
Kilojoules per mole. No, not per mole. It's just kilojoules. Sorry. Just kilojoules.